Hello again. So in this video, we're going to go over part two of bond hybridization day one, just to review what we did last time, right? These are the three take-home messages, not obviously complete sentences, but we're going to put into context now. So valence electrons are the electrons involved in bonding. Half-filled suborbitals are the only suborbitals that can form covalent bonds, and to fill, or rather to create those half-filled suborbitals to form these bonds, electrons can be promoted. So we're going to continue to go over that in these different examples. So beryllium chloride formed or requires two bonds, right? Beryllium chloride requires two bonds. The ground state for beryllium, remember we're just considering beryllium here. So the ground state orbital diagram for the valence electrons of beryllium look like this, right? Beryllium is right here. 2s is completely filled. Okay. It doesn't have any orbitals, any suborbitals that can create a bond, right? These are all empty and these are all full. So it's going to promote into what's called the excited state. So this electron is going to move into the 2px suborbital, and that's what it looks like in this excited state. It's still at different orbitals with different energies. 2s is slightly lower than 2p, but to create a bond, we need now a hybridized state. This hybridized state is not 2s, it's not 2p, it's simply sp. S and p because one electron came from s, and another one, so that one came from s, and this one came from p, and it's now called sp, right? And it's now ready to create those bonds, those two ligands with chlorine, right? So here we looked at an sp hybridization. Didn't want that. Let's erase that. We're going to continue to go through different kinds of hybridizations. This one, I thought I erased it. This one is the sp hybridization with two hybrid orbitals. Next is the sp2 hybridization. This is going to have three hybrid orbitals. And another example, switch pens, okay, is BCl3. So this trigonal planar molecule, boron trichloride, begins with, so boron is ground state, looks like this. Two electrons in the 2s and one in the 2p. It looks like this, right? We have three ligands, three bonds. In its ground state, we only have room for one bond. What do? We promote. So your excited state looks like this, with this one electron here being moved into the 2py and changing its spin, spin up, spin up, spin up. We now have these three required half-filled suborbitals that will be used to create those three bonds. In its hybridized state, when they merge, right, they then create an s and two p's. This was the s, this was a p, and this was another p. Put them together and it's sp2. And that gives us our sp2 hybridized state. We'll talk more about this in our next topic, but this is an unhybridized p orbital. We don't need to draw this, it does not hybridize because there are no electrons there. Right, we'll talk about what unhybridized means in day two of bond hybridization. Right, so our next hybridized state is the sp2. Okay, sp3. Now we already started this, did it to start talking about bond hybridization, but carbon, just to show you again, carbon looks like this. Its valence orbitals look like this. Orbital diagrams look like this. It has two electrons in the 2s and two in the 2p. We know that this is a tetrahedral molecule, right? To review how that looks like, it's in its Vesper shape, roughly like this, right? Filled in, coming out at you, behind, looking like that. Right, so we have 1, 2, 3, 4 ligands. In its ground state, we only have two half-filled suborbitals. They can't form these four. So what do? You should be thinking we promote into an excited state. This electron is going to move into the 2pz. So it does change its spin. The hybridized state just means these are all going to come together. We're going to have one electron from S and three from P, which gives us sp3. sp3, right? This one electron here, there. If this is going too fast, feel free to pause. It's the beauty of these videos. Okay, so this is now your next hybridization states, and that is your sp3. Okay, next. These are now your expanded octets. So these occur when you have more than your 8 valence electrons. And we know that that can happen. So let's look at this example. We need 5 ligands, 5 connections here, 5 suborbitals with only half-filled states. So 3s has 2. This is phosphorus's ground state. 3s has 2. 3p has 3. So that's a start, but we don't need 3, we need 5. So as always, what do? We promote, but this time we promote always to an empty suborbital. Well, the closest suborbital that is empty is then in the 3d. So that would allow us to then have our 5 required hybrid orbitals, 1, 2, 3, 4, 5. Like before, you have 1 electron in the s, 3 in the p, 1 in the d. That's going to give us didn't mean to draw that. That's going to give us an sp3d hybridized state. So it looks like this. They combine and we have 1, 2, 3, 4, 5 electrons. One from here. These 3 are all here, right? And that 1d right over there. That's now sp3d. Okay, sp3d2, very similar again, within this expanded hybrid, or in this expanded valence shell. We have completely filled suborbital here, completely filled 3px here. We need 6 ligands. We don't have that. We have 1, 2. That's all we have. So what do we do in this case? Well, let's promote 1. Okay, so promoting 1 would mean we now have this has freed up. This is half filled, and now this is half filled. We haven't talked about this yet. So that then allows 1, 2, 3, or rather, if this moves here, it allows for 1, 2, 3, 4. But we don't need 4, we need 6. That means we have to promote not just this one electron, but the following one as well. So that will move here. So it's 2 electrons promoted in this case, which will give us our 1, 2, 3, 4, 5, 6 required orbitals or half-filled suborbitals. Because there are 6, 1 came from S, 3 came from P, 2 exists now came from D. They now look like this, or it's now called sp3d2. That is I believe, our last hybridized state, sp3d2. Oops. Okay. Good. In this example, NH3, if you recall, looks like, oh, let's get our pen going again. Ammonia looks like this in its Vesper shape. Right, this is a trigonal pyramid shape. We need 1, 2, 3 ligands, and we need a lone pair. So in the examples we've done, we've only looked at non-lone pair central atoms. This is the first time looking now at an example that we have both. We have lone pair and shared pairs of electrons. All right, so in this example, for nitrogen, we have 1, 2, 3, 4, 5 electrons in its ground state. Remember, this is for nitrogen. In nitrogen, we need 3, right? 1, 2, 3 ligands and 1 lone pair. So in our excited state, we have no change because we have what we need as it is. So 1, 2, 3 electrons, half-filled suborbitals create the conditions necessary for a covalent bond of 3 ligands. And this electron pair, this lone pair, is right here. This is our lone pair. Energetically is getting prepared to bond. It is in an excited state, except there's no movement of electrons. We need to hybridize though. So for any kind of bonding to occur, we still need these hybridized states to happen. So we still have well, not just one electron here, two electrons here into the s suborbital. Then we have one, two, three electrons from our p's come here. Now we're counting then at the number of orbitals. We're counting the number of orbitals. It's s here, 1, 2, 3, right? So it's still an sp3 orbital state. So you can look at it as a number of electrons to create these. Probably best to look at it as the suborbitals that form the hybridized state. So there's one s suborbital and there are three p suborbitals, still creating an sp3 hybridized state for nitrogen to create ammonia. Okay, so how does the ground state, excited state, and hybridized state look like for ICl3? Now, normally it'd give you some time to answer this. Pause the video so you can give it a shot. I've given this to you already. We'll answer next. Okay, so this is iodine. Let's look back at what iodine should look like. We need 2 lone pairs and 1, 2, 3 ligands. 2 lone pairs and 3 ligands. In its ground state, in iodine's ground state, right, we have 1, 2, 3 lone pairs and 1 half-filled suborbital. We need 3 ligands, so let's promote this one. Likely going to go there, right? That's your excited state. Then it has to hybridize, right? You're ready now for it to create these bonds. It needs those 3 ligands, 1, 2, 3. And look, you've created the conditions necessary for 2 lone pairs. 1 here and 1 there. Here and there. And it looks like that. 1 suborbital from the S, 3 from the P, and 1 from the D gives us an sp3d hybridized state. Okay. So how to do this in questions that you'll be practicing yourself. Here is a bit of the procedure. Again, I'm not going to read it for you. Practice it, refer back to these notes, refer back to the procedure. Let's instead actually do an example. So this is BH3, a boron trihydride, and it says to draw, your instructions say, draw a Lewis structure. So it looks like this. No lone pairs, just 3 ligands. Now, boron right here, has a 2, so in its valence it has a 2s2 and 2p1. So its ground state looks like this. I can highlight this and make it a bit smaller. Okay, so ground state for boron, 2s, 2px, 2py, 2pz. 1 here, 2 there, and 1 more there. That's all it has. In our excited state, we're going to need 3 ligands, right? So we're going to promote this one here, and our excited state will look like this. Now we have the 3 half-filled suborbitals we need. I'm going to move this timer somewhere else. That's fine. Our hybridized state then just combines all of these. We have these 3 suborbitals, 1, 2, I'm not going to show the empty ones, 1s, 2 p's, we get an sp2 hybridized state that looks like this and is ready to bond with your hydrogens. Spin up, spin up, spin up. Okay? For you to review, they'll have different shapes, different orientations. They look like that. You can review that yourself to look back at the different hybridized states that we covered. Great simulation on this link. But we're essentially done. Day 1, part 2 of bond hybridization. Right, work on this. I believe I have an answer key for this, but attempt it yourself. It may or may not be posted, so let me know. Try it yourself. This needs practice, guys. We really have to practice this. So practice this, connect with me, ask questions, and we can take up answers next time we meet.